Hello, everyone. First of all, I greatly appreciate this invaluable research opportunity given to me by the RESESS program by UNAFCO. My name is Shamsuddin Ahmed, Shams for short. I am a geology undergraduate at Appalachian State University in North Carolina, and my talk is going to be about the occurrence of gold in the Cross Mine in Boulder County, Colorado. Before I start, I would like to give a special thanks to my co-authors, as without them, this project would not have been possible. I would also like to acknowledge that sample collection and analytical work for this project was done on land that originally belonged to the indigenous Ute and Cheyenne peoples. Here is a general outline of the talk, and at the end of the talk, hopefully we have some time for questions and comments. Okay. So the occurrence and sequestration of precious metal minerals in the Cross deposit is not very well understood, and better knowledge of the deposit will help improve exploration efforts here and elsewhere. Thus, it was our aim to improve our understanding of the occurrence of gold and silver in the deposit, as well as the formation of the deposit, which will also help in exploration efforts. The Cross deposit is a magmatic hydrothermal deposit, which is a hydrothermal ore deposit in which the aqueous solutions were derived from hydrous magmas. But the origin and formation mechanisms of the deposit are still very highly debated. So this is where the Cross Mine is located in Boulder County, just west of Nederland, and in the Grand Island Mining District, which lies on the Colorado Mineral Belt, which is well known for its many resourceful mines. Geologically, the Cross Mine is located on top of Precambrian Idaho Springs gneiss, which has been intruded by early tertiary igneous intrusives, namely the Caribou Monzonite and gabbros and lampreyfires. Now for some background info, the main rock units that we're concerned with are obviously the Idaho Springs gneiss, which is a quartz biotite sillimanite gneiss formed from a shaly protolith and is also some of the oldest rocks in Colorado, as well as the Caribou Monzonite, also known as the Caribou Stock, which is the main intrusive rocks in the Grand Island Mining District associated with the laramide orogeny. Precious metals, gold and silver, occur in veins in both these units. So the Grand Island Mining District represents a magmatic hydrothermal system, which is a system in the Earth's crust that are related to hydrous magmas, mainly at convergent plate boundaries that provide heat and mass transfer for the formation of ore deposits, including base, precious, and rare metals. Hydrous magmas provide hot aqueous fluids that flow through the host rock, which in this case is the Idaho Springs gneiss. And as those fluids course through their host rock, they alter the rock in a process known as hydrothermal alteration, which changes the primary chemistry, mineralogy, and texture of the host rock. And there are well-defined zones of alteration, the identification of which can be quite influential in a reconnaissance survey such as this one. In the schematic diagram to the right, you can see the different deposit types in a magmatic hydrothermal system. We do not yet know exactly which type of magmatic hydrothermal deposit the Cross deposit is, but it has some similarities to porphyry copper deposits, which are one of the most well understood deposits that occur in such a system. The Cross deposit is somewhat similar to porphyry copper deposits, as mentioned before, but they're formed by similar processes in similar environments, but have vastly differing rock types that are involved in those processes. So they're not exactly the same. And unlike copper porphyry deposits, the Cross deposit is not centered around copper porphyry stocks. It does not have stockwork veining and is generally richer in precious metals. High grades of gold, meaning high concentrations of gold, are known to occur deeper in the system at the Cross Mine. So sampling strategy, we collected samples from the Cross Mine belonging to the Idaho Springs gneiss that showed high precious metal concentrations based on existing geochemical analyses. And we targeted them for subsequent analyses. We investigated a subset of 6 samples from across the deposit as part of a larger study, which we will discuss later. Some analytical methods that we used are, we used all the instruments that we used were used at the MMC facility at the Colorado School of Mines. We used handheld XRF and micro XRF mapping to evaluate the location and distribution of ore minerals prior to sample preparation. Then we prepared thick sections before running them through the SEM-based automated mineralogy instruments for getting false color mineral maps. And then finally, we ran the samples through FESEM, BSE imaging, and EDS analyses to look for gold and silver, to image gold and silver. So in this slide, you can see the results of our micro XRF mapping. Here you can see the house rock, which the arrow points to, is sort of darker colored, and it is rich in aluminum and silicon. The aluminum map is a little harder to see because of the choice of color, but trust me, there is aluminum in there. The alteration halo, which forms around the veins, as discussed before, is indicated by this blue arrow. And as you can see in the maps, it is primarily rich in potassium, very rich in potassium. And so we also found at least 2 kinds of veins in the samples. And the first type is this calcium and manganese rich vein, which seems to be cross-cut and displaced by this newer vein, which is primarily rich in iron and sulfur. We also found some gold and cobalt. Over here, you can see some cobalt grains, discrete cobalt grains, as well as some tiny gold in the maps. So here you can see the automated mineralogy false color mineral maps, and you can see the different vein types here. These are the calcium and magnesium rich veins that we mentioned before. These are here shown as the carbonate veins, and these are the veins rich in iron and sulfur, which are quartz pyrite veins. You can also see the different kinds of alteration associated with these veins. Most of them have similar alteration styles associated with them, which is primarily rich in potassium feldspar, which is this tealish color you can see around these veins, but with only one exception in this sample right here, which has a more darkish magenta color surrounding the vein, this quartz carbonate vein. And that could be sericitic alteration. And precious metals were primarily found in these quartz pyrite veins. So finally, gold. We found gold in multiple samples. In this sample, you can see gold associated with electrum, in the form of electrum associated with galena and pyrite in a quartz vein. In this sample, you can see silver with electrum or gold-rich silver, native silver as well, which is associated with barite in this quartz vein. Other minerals that are associated with the precious metals are sphalerite and galena, as well as chalcopyrite. We also found silver as a trace element in sulfosalts, which are complex sulfide minerals. So to summarize, The host rock is abundant in silicon and aluminum with minor strontium. Common minerals that occurred in the host rock are potassium feldspar, plagioclase, quartz, muscovite, amphibole, biotite, and chlorite, which agrees with what we know about the host rock being a quartz, biotite, sillimanite gneiss. There are two main types of veins that we saw: carbonate veins that are rich in manganese and also contain iron oxides and barite, and quartz pyrite veins, which contain gold and silver. There, we saw two alteration halotypes, the first being potassic, dominated by potassium feldspar and associated with both carbonate veins and quartz pyrite veins, and cerasitic, which is dominated by cerussite and associated with the one quartz carbonate vein in one of these samples. The carbonate veins seem like they formed first based on cross-cutting relationships, and followed by the quartz pyrite veins. And precious metals, gold and silver, occur in the quartz pyrite veins, which is associated with potassic alteration. Further analyses, including cathodoluminescence, field inclusion studies, and other studies will be done to get more in-depth understanding of the vein mineralogies, textures, and history in future studies. Similar deposits and future studies. Similar deposits to the cross deposits are the Toromocho porphyry copper molybdenum deposit in Peru, as well as the porphyry-related polymetallic gold and silver vein deposits in Central City, Colorado. This study was part of a much larger study, which will study the origin and formation mechanisms of the magmatic hydrothermal system, known as the Grand Island Mining District, and improve our understanding of the existing alteration styles and the extent of alteration present, which will also aid in exploration efforts in the district and elsewhere. Some people I would like to acknowledge are Dr. Katharina Pfaff, my research mentor, who also provided the opportunity to work on this project, and Kelsey Livingston for help with the analyses and data interpretation throughout the project, and Joel Johnson, my communications mentor, for help with writing, and Sean Muller for access to the cross-mine and fieldwork. I would also like to thank the NSF for supporting this work. This work was conducted within the NSF IUCRC Center for Advanced Surface Earth Models, CASERM, which is a joint industry university center between the Colorado School of Mines and Virginia Tech. Thank you so much for your time, and I'll try my best to answer any questions and comments you may have.
Great job, Shams.
Thank you.
If you have any questions, you can either type them in the chat or raise your hand and unmute yourself. Yes, Lon?
Shams, thank you very much. So you started the talk saying that you thought it was a porphyry deposit, and then you came back around to that at the end with the similarities. What aspects of your findings reinforced that it was a porphyry copper deposit, or excuse me, a porphyry deposit, not copper, and that, but what was it that made you still uncertain about whether that was the actual type of deposit you had? I guess I didn't make this clear in the beginning, but it is definitely not a porphyry copper deposit, because there are some significant differences. The main differences being that the rocks involved are vastly different. So in this deposit, the rocks involved include monzonites and gneisses. But in porphyry copper deposits, the main rocks involved are porphyry copper stocks. And so also this deposit does not have stockwork veins, which is one of the main characteristics of porphyry copper deposits, as well as being this as well as this deposit is more rich in precious metals, which is lower relatively in porphyry copper deposits. So those were the main differences, and so we can't conclude that it is a porphyry copper deposit yet, and we're still uncertain about what kind of deposit it is. And hopefully future studies will shed more light on it.
Great, thank you.